Oh, well, let me begin now. So, coherent Raman scattering and coherent anti-Stokes Raman scattering are nonlinear optics techniques suited for imaging, sensing, and detection without labeling or distraction. Implementation of ultrafast pulses in coherent Raman scattering and Cars microscopy and spectroscopy bring advantages of high peak power, high three-dimensional spatial resolution, and femtosecond time resolution to monitor vibrational dynamics. Femtosecond stimulated Raman scattering and Cars microscopy and spectroscopy have been femtosecond coherent Raman scattering and coherent anti-Stokes Raman scattering spectroscopy and microscopy have been widely used and nowadays advanced towards solving tasks related to single molecule spectroscopy, molecular specific imaging, sensing traces of molecules, remote detection, and many more. To bring coherent Raman scattering and Cars spectroscopic techniques to a new level of chemical sensitivity and specificity, we address quantum properties of material and through crafting ultrafast pulses optimize light interaction with matter on quantum level. In molecules, vibrations within the electronic potential are quantized. And here they are presented as two horizontal lines showing the ground vibrational state 1 and the first excited vibrational state 2. Coherent Raman scattering spectroscopy is based on the stimulated Raman scattering process, which implies two frequencies, omega pump and omega Stokes, within the incident ultrafast laser pulse that interact coherently with the molecule and stimulate transition at Stokes frequency. Coherent anti-Stokes Raman scattering, schematically shown on the right side, is four-wave mixing process in which anti-Stokes radiation is being stimulated and generated to create coherent anti-Stokes Raman scattering signal measurable in the experiments. It is blue shifted frequency component with respect to the relay line. Well, the molecular state described in quantum mechanics within the quantum mechanics theory, and here it is presented as a superposition of two vibrational states under consideration with the coefficients A1 and A2, which when they are, squared provide the probability of molecule to be in one state or another. According to Maxwell's theory, Raman field's propagation is proportional to the induced macroscopic polarization in the medium, which in its turn is proportional to the microscopic quantum properties of the material, quantum coherence, carrying information about the phase relationship of the vibrational states involved, in this case A1 and A2 complex conjugated. Thus, crafting laser pulses to maximize quantum coherence is the way to control quantum effects in the Raman scattering process and its optimization, leading to qualitatively novel outcomes. This is the principal concept to quantum control. Well, I started my work on quantum control in Raman spectroscopy with the publication in Physical Review A in 2004. In this work, I explored a possibility to study, to selectively excite well, closely spaced vibrational modes in stimulated Raman scattering. I designed laser shapes to selectively enhance or suppress excitations of the symmetric and asymmetric Raman modes in methanol molecule. Later, my focus shifted to a study of phase modulated pulses to control Raman excitations. To enhance car signal and suppress the background noise, we developed a series of methods based on adiabatic passage. These methods facilitate the identification of species and the detection of coherent signal from traces of molecules. Later on, this year, let's move on. This year, a paper in Kempf's Letters is a culmination of a series of works in this field over the last decade. We developed a control scheme to perform adiabatic passage in the 4-wave mixing process. Here, Wigner plots show the linearly chirped pump, Stokes and Prof pulses shaped to maximize quantum coherence in the vibrational state in the target molecules. Notably, the Prof pulse has to be shaped as well to achieve adiabatic passage. Implementation of such shaped laser pulses provide the maximum value of coherence in the target molecules, shown in blue color for a broad range of field intensities, the chirp rate on the x-axis and the Rabi frequency on the y-axis. At the same time, coherence in the off-resonance system, representing the background noise, is strongly suppressed, and it is shown in red color also for the broad range of field parameters. These results are obtained for the methanol molecule shown in the middle. The results of broad validity, and they have application to detection of trace amounts of SARS-CoV-2 proteins that have a characteristic frequency at 4965 terahertz, as this calculation of infrared spectra show. So the methodology permits monitoring air quality related to COVID. So this methodology has a number of advantages, and the major of them is high molecular selectivity and specificity, and also significantly increased signal-to-noise ratio compared to non-shaped pulse techniques by 3 to 6 orders of magnitude. Well, moving on, we studied the impact of the decoherence on the controllability of selective excitation of Raman transitions. And decoherence is inherently present in the molecules interacting with the environment. And to mitigate it, we use two phase-locked pulse trains, here shown by black omega-3 Rabi frequency on the figure. Like figure shows the result of application of two sequential pulse pairs and this time. So first pulse pair generates maximum coherence, shown in red, which is subject to decrease due to spontaneous decay, red curve decrease, and collisional dephasing. That's the blue curve, shows how decay occurs due to the collisional dephasing. Then if the pulse train period is the same as vibrational and relaxation time, then next pulse pair arrives and restores population of the excited state and coherence lost to spontaneous decay. Thus, it is possible by implementing a phase log pulse train with the repetition rate same as the spontaneous decay rate to preserve coherence at the certain level and have significant signal to, which may be measured, to be measured. Well, phase log pulse train generates optical frequency comb. Optical frequency comb is a novel and unique tool for high precision spectroscopy analysis. Optical frequency comb possesses a number of parameters that may be used as control knobs to manipulate molecules, molecular dynamics on femtosecond time scale. These are the pulse train period, which in the frequency domain, where the frequency comb is presented, correlates with the spacing between the sharp peaks in the comb in the radio frequency. So 1/t is omega r. So another control parameter is offset frequency f0. Then omega n, which is optical frequency with n large integer multiple. Tau, which is the pulse period, pulse duration, and field amplitude, and certainly the phase of the field. Frequency comb has been recently applied to coherent anti-Stokes Raman scattering spectroscopy. The novelty of our work is in the use of the control techniques in application of optical frequency comb. We test all the parameters discussed above, and we imply the modulation across individual in the form of the sinusoidal function. Here, the upper equation, not many of them will appear in the future. A is the modulation amplitude, and omega is modulation frequency. The figure shows, sinusoidally modulated optical frequency comb on the upper panel, and the lower panel shows the spectral counterpart, the Fourier transform, where a series of the combs are generated with the spacing proportional to the omega. So such modulation broadens significantly spectrum of the frequency comb compared to the standard of optical frequency comb shown in the bottom. Well, we applied sinusoidal modulation of the phase starting from the time domain and starting from the frequency domain, and we observed uniformity of the structure of the field and the interaction with the molecules. Here is the example of the modulation, sinusoidal modulation starting from the time domain. The left figure shows a single pulse electric field, which is sinusoid, sine modulated, cosine modulated, and without modulation. We see a significant difference in the phases, which results in a dramatically different response of the molecular system subject to interaction with such phase log pulse train. The upper curve, so we consider, if to look at the bottom left, we consider Raman configuration with 7 vibronic states involved. Now the right upper panel shows the dynamics in such a Raman configuration subject to the interaction with temporal cosine modulated optical frequency comb, and we observe a piecewise population transfer from the initial to the final target state, because the pulse area of the applied pulse is in fact very small, 0.02 of pi. So many pulses have to be implemented in order to perform population inversion. In contrast to this successful population inversion, the temporal sign modulation did not reach this goal. So that's the temporal cosine modulation that creates quasi-dark states, resulting in complete population transfer. This response is analogous to the one in the stimulated Raman scattering technique. Well, the parity of the modulation is the key parameter that controls population transfer, as we have seen from the temporal modulation example. Here is the real and imaginary components of the field are shown for the sine modulation A and B, and cosine modulation C and D. The asymmetry is observed on the figure B, right, of the field, imaginary part of the field, that induces different interference pattern in the molecules, resulting in the creation of a quasi-dark state and complete population transfer to the target state, as opposed to the dynamics induced by the cosine modulation, which is even chirped. Well, here the Wigner plots of these 4 cases of the modulated optical frequency comb are shown on the right panel. A and B show the time modulation, sine and cosine, and C and D show the frequency or spectral modulation, sine and cosine. The adiabatic passage due to the quasi-dark state generation is achieved by the field shown on B and C figures. So cosine temporal modulation or sine spectral due to the parity of the chirps respectively. So the left panel shows the result of application of this B and C fields to the 7-level Raman configuration. The evolution is long enough to reach the steady state, which shows maximum coherence. This regime is ultra cold regime, where the collisions are very slow, 10 to the 4th hertz. We implemented the concept of quantum control in combination with the phase-shaped optical frequency combs that are formed by phase-log pulse trains for remote detection. And we investigated the range of the laser parameters that drive the limits for the detection. We estimated the number of detectable photons in the backward direction, depending on the key parameters: the distance to the detector diameter of the beam, and molecular concentration. So the optical frequency comb demonstrated a possibility to mitigate decoherence in the air upon propagation large distances. Well, here are several key areas of applications where quantum control approach leverages sensitivity and resolution. I mentioned many of them already in previous discussion. Now I would like to discuss another application of quantum control, which goes as far as for quantum sensing, and it is about the generation of quantum entanglement using the platform of trapped Rydberg atoms. Rydberg atoms are atoms in which electron is excited to a very high orbital, the principal quantum number maybe equal to 40, 60 and more. This results in the strong induced dipole moment. And such Rydberg atoms are strongly interacting with each other through this dipole interaction or through a weak van der Waals type of interaction. Such systems are certainly strong candidates for the quantum computation and have been explored heavily through the recent years in this direction. Quantum entanglement involving coherent superposition of distant states is one of the most striking features in quantum theory. However, realization of quantum entangled state is extremely challenging because they are very fragile. So we propose a quantum control methodology to create multi-particle or multipartite, in other words, entangled states with predetermined properties. Particularly, we look at the states, the so-called W state or Green-Horn-Zillinger states, GHZ state. They are shown for the 3 atomic case on the left side after the text. So we consider a chain of atoms, alkali atoms like rubidium-87, which are, each atom is represented by the 3-level ladder system shown on the right panel. So each atom is excited from the ground to the Rydberg state via 2-photon Raman type of excitation using 2 circularly polarized linearly chirped pulses. And such 3-level ladder systems representing each atomic atom in the trap are coupled via Rydberg states by the coupling parameter V. Okay, so we have calculated the fidelity of the Green-Horn-Zillinger state generation for a broad range of the field parameters. So here, and demonstrated that GHD state may be achieved, may be generated using adiabatic passage. So we generated it with 2 linearly chirped, equally chirped pulses having the same overlapping Rabi frequency. So the fidelity of the GHD state formation is shown in the upper panel A, and the optimal values of fidelity within 0.99 range are highlighted with the contour plot. The lower point panel shows the population difference of the 2 states that contribute to the GHD state, and 0 values correspond to the case when they are equal, together with the information of the fidelity at the same range of the field parameters. This indicates upon the equal, the phase relation, high phase relationship between atoms in the trap. Now, the right figure shows the dynamics of the creation of the GHD state, which obviously shows adiabatic passage, and this dynamics occurs for the high fidelity 0.99 parameters are presented here. So we also generated the W state, and this mechanism for the generation of W state is inherently non-adiabatic due to the properties of the W state and the required states selected from the total manifold of the many-body states. And the fidelity shows high fidelity in blue, islands in the contour plot as a function of the chirp rate and the Rabi frequency. Here, the black curve draws the contour where all three states contributing to the W state formation have same population. So that's indeed the W state is demonstrated by the black curve. The upper panel shows the dynamics of the creation of the W state, and this dynamics occurs for the values of the fidelity, one of the highest in this calculation. So we observe significant Rabi oscillations indicating upon non-adiabatic regime of interaction during the transitional time. So quantum control of multipartite entangled states generation involving coherent superpositions of trapped Rydberg atoms is presented based on the two-photon passage on the selected state manifold using circularly polarized and linear pulses. And the selectivity of states is achieved through the choice of the one-photon detuning, the ratio of the Rabi frequency to the collective coupling strength V, which I showed in the beginning of this discussion, and the chirp rate. Well, with this, I would like to acknowledge contribution from my PhD students, current and those who have graduated during previous years, and the funding agencies that support our research, NSF, Alexander von Humboldt Stiftung, and the Office of Naval Research. And here is my information for contact. Thank you very much for your attention.